All right, good morning, everybody. Today we are going to continue with multiplicity. And so last class period, that's what we spoke of. And I just have a little bit more exploration activities with multiplicity. But first, just to review, there's something called right hand and left hand behavior. We call that end behavior. And so you could very well just type this in Desmos and see what it looks like. But I'm hoping that you remember the rules from last time. And the rules from last time says you identify your degree. And so you would say degree is 5. Actually, let's start with the leading coefficient. The leading coefficient is negative, so I know it opens down on the right. And I would look at the degree, and the degree is odd. So if the degree is odd, whatever it did on the right, it does the opposite on the left. So it's going to open up on the left. Now, the way we say that is as x goes to the left, it goes up, the function. As y goes to the right, it goes down. And so I'm going to write this. This would be as x travels to the left forever. So as we go to the left, the function goes up. Forever. And then for the other one, I would say as we go to the right forever, that'd be positive infinity. It goes down forever, that'd be negative infinity. So as x goes to the right, the function goes down forever. And then it does stuff in the middle. We call those, could be some possible turning points. Okay, the next one, I look and I say, okay, my leading coefficient is actually positive 1. So if it's positive, it opens up on the right. If it's negative, it opens down on the right. And then you look at your degree, and the degree is even. So even degrees repeat themselves. So because it opened up on the right, it's going to open up on the left. And so the way I would say that, I would say as x approaches the left, it goes up. So as x approaches negative infinity, the function approaches positive infinity. And as x approaches positive infinity, the function approaches infinity. So let me write that down. As x approaches negative infinity, the function also goes up. That'd be for the left part. And then for the right, as x approaches infinity, as x goes to the right, the function also goes up. Okay, so that's what we did. I think it was last class period or maybe 2 times before that. That's a nice little review. So we're going to look at graphs a little more deeply today. And so what I have here is I have 4 graphs, and I have the equation for each. And what I want you to notice is that when the solution is when the factor is x minus 1, the solution is 1. When the factor is x plus 5, the solution is negative 5. So how many solutions does this have? That's the degree. And if you look, you have 1, 2 solutions. So I'd say this is a degree. You could also get that from the equation because you got x to the first, which would be x squared. The negative is what makes this upside down. And then something called a turning point. So it's, if you're traveling on this parabola, you're going up, 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 up. You reach to the top where the slope is 0, and then you start going down. So I would say this has one turning point. And where does it turn? It turns right there. Okay, the next one, I see that I have a solution at 1, 3, and -2. 1, 3, and -2. Okay, so what's my degree? I have 1, 2, 3, or I could count them here. X to the 1, x to the 1, x to the 1 would be 3. How many turning points do I have? Well, I'm coming down, turn, turn. So I have 2 turning points. Here, I have a solution at -1. I have a solution at 2 twice. So notice whenever you have an even solution or even multiplicity, that's when it comes up, touches, comes back down. And then I have a solution at 4. And so when I'm counting my solutions, it would be 1. This is going to be an even amount. We don't know exactly how many. And then that would be 1. So for this one, I can't just go 1, 2, 3, 4. It's probably 4. I need to look at the equation, which is 1, x to the 1, x squared, x. So that'd be 1, 2, 1. 1, 2, 1 is 4. I got x to the 1, x to the squared, x1 makes x to the 4. So the degree is 4. How many turning points? Turns, turns, turns. So I say 3 turning points. Okay. Here, again, because it comes up, touches, comes back down, I know that this has multiplicity. This has multiplicity here too, of at least 2. It's going to be even multiplicity. It could be 2, 4, 6, 8. We don't know. So if I look at the equation, this is saying that -2 is a solution twice. See? This is saying that 3 is a solution twice. So if -2 is a solution twice and 3 is a solution twice, that makes a degree of 4. X squared makes 4. Now how many times does this turn? We're going up, turns, goes down. Turns, goes up, turns, goes down. So I believe I counted 3 turning points. And so you may notice that there's a relationship between the degree and number of turning points. Okay, and I'm not going to fill this box in for time, but you can see 2, 1, 3, 2, 4, 3, 4, 3. So the number of turning points isn't always 1 less than the degree, but it's at the most 1 less than the degree. Okay, so well, I'm not going to focus on turning points, but it is something important to know. And then here's some more examples. Notice, this is really what I want you guys to see, is like this one has a solution at -1. See how that's an even degree? Anytime it's an even degree, it comes up, touches, comes back down. It always has multiplicity of at least 2. Same thing is happening at this one, the x minus 2. And notice it's x minus 2 to the square. So that's a solution of 2. And notice, again, it has even multiplicity. And then this one is just a linear factor that happens once. That's when it crosses just once. And that solution would be 1/2. Okay, which you can see 1/2 right there. So that's really what I want you guys to see from this graph. The next one, so the solution is -1 right here. And we have multiplicity of 2. That's what makes it come, touch, come back down. But then it's kind of interesting when the multiplicity is 3. See how that's a 3? So x minus 3, solution will be 3. That's when it kind of comes up, and some people call that a squiggle. and then it goes up. So anytime it's an odd degree, I shouldn't say odd degree, anytime it has odd multiplicity, that's when it does, some people call that a squiggle. So like right here, there's a squiggle. So because there's a squiggle, I know that 1, or I should say -1 is the solution. X plus 1 is the factor. It has to be of odd multiplicity. And that's why it's odd, see? But when I look at the solution 2, I see that it's, and some people call this a bounce. So if 2 is the solution, then x minus 2 is the factor, and it has to be of even multiplicity. And that's why x minus 2 is of even multiplicity. And then anytime it just goes straight through the graph, or I should say the x-axis, then we know the multiplicity is just 1. So there you go. So what I want you guys to get used to is if you see a bounce, you should be looking, that'd be what, x plus 2 is the factor. You should be looking for even. Anytime you see a squiggle, so I'd call this a squiggle, you should be looking for odd, and so that'd be 0. Anytime 0 is a solution, that's just x. So that'd be x to the 3rd, or x to the 5th, or x to the 7th. That's what this part comes from. And then I would say that 2 is a solution and it's a bounce, so it's going to be even multiplicity. So it's going to be x minus 2 with an even multiplicity. Okay, so looking at the roots of the graph, and that's what we call solutions. Sometimes the graph crosses the x-axis, sometimes it bounces off. Can you come up with the generalization? And again, for time, I'm not going to write, but we just said that if it has like an odd multiplicity, it does a squiggle. And if it has an even multiplicity, it does a bounce. And if it has to the 1st degree multiplicity, that's when it just goes straight through the graph, like right here. Okay, so that's really what I want you guys to make sure you understand. So here's some facts. So it can be shown that for a polynomial function of degree n, then the following are true. The function has n real zeros, and the graph has at most n minus 1 turning points. So we talked about turning points at the beginning of this lesson, and we said the number of turning points is always at the most 1 less than the degree, so it could be less. And then here's more, and I'll let you read that yourself. Multiplicity, also called repeated zeros. A factor x minus a to the k yields a repeated 0, x equals a, with multiplicity k. In other words, you could look at the exponent, and that tells you your multiplicity. If your multiplicity is odd, the graph crosses the x-axis. It's usually a squiggle, unless it's to the 1st. If it's even, the graph touches the x, but does not cross the x. And we call that, some people call that a bounce. So what we're going to do here, here's some steps on how to graph a polynomial. Again, I'll let you read that yourself. And then this problem, so they want us to describe the end behavior, find all the real zeros, determine the multiplicity of each 0, and then sketch the graph. You guys aren't ready. Actually, you guys know how to factor this. We could do this one. And so this is review. It's a quadratic. So what I would do is I'd say, okay, what multiplies to 25 but adds to 10? And we did this last chapter. So what multiplies to 25 and adds to 10? Let's see. That would be what, 5 and 5? I don't know why. There we go. So then I would say my factors are x plus 5, x plus 5. So that'd be x plus 5 squared. So first, A, describe the end behavior. Well, this is my leading term. Because this is positive in front, I would say as x, I know it's going to go up on the right because of the 1. And because of the even, it repeats itself on the left. So it's going to go up and up. So I would say as x approaches the left, my function goes up. And as x approaches the right, my function also goes up. So in case you haven't caught on, this will always be the same. This is as x goes to the left, as x goes to the right. What changes is this part. My infinity needs some surgery. Still doesn't look very good. 2, find all the zeros. Okay. Well, that's easy. Negative 5 is a 0. So I could go here to negative 5. And let's see, determine the multiplicity. Multiplicity of 2. And then I'm not going to worry about the turning points. And then we're going to sketch the graph. And we're just going to do a rough sketch. So I know it opens up. I know it opens up. I know it's going to do a bounce here because multiplicity is even. So it's going to come down, do a bounce, go back up. And this is a rough sketch. It doesn't look exactly like that, but all I want you to know how to do is a rough sketch at this point. Okay. Let's do another one. We might come back to 2 and 3. They are not factored. They're in what's called standard form. I want you to know how to work with polynomials that are already factored. So we'll start with number 5. Number 5, let me think. What would the leading coefficient be? So my leading coefficient is going to be x to the third. Make it negative, so it's going to be negative x to the third. And so the negative means it opens down. The odd means it does the opposite on the left. So I know it's going to go like something and then go down here somewhere. And so I would say as x approaches the left, my function goes up. And as x approaches the right, my function goes down. Now, what are my solutions? My solutions for x plus 3, the factor is x plus 3. I would say negative 3 is a solution. Multiplicity, I was saying that wrong the other day, of 3. So in case you don't remember, anytime it's to an odd degree, it's like a squiggle. I have no idea how to spell squiggle. And then for x minus 2, the solution is going to be 2 multiplicity of, how many times does that happen? 2. So that's going to be a bounce. is what some people call it. It's not really very mathematical sounding. And so let me think. Okay, so I know -3 is a solution no matter what. 1, 2, 3. I know that 2 is a solution. Okay, so it's gonna come down, squiggle, and then it's gonna have to come back up to reach that, and then it's gonna bounce, and then it's gonna come back down. So right here, you kind of have to pre-plan. So it's gonna start up here somewhere, and it's gonna come down, do like a squiggle, which I don't know if I drew that perfectly. And then it's going to come up here and do a bounce. And then it's going to go down forever. So that's a rough sketch. All I want is you to have a rough sketch. And don't be afraid to check your work. And so what I'm going to do is I'm going to type this in Desmos real fast just to double check. Because even I'm wrong sometimes too. Let's see. So my function was negative x plus 3 to the 5th x minus 2 squared. Yeah, I mean, you can see theirs is a lot skinnier right there. Mine's a little bit wider, but it's the same idea. See, it comes down, does a squiggle, comes down some more. Theirs went way, 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 way down. Oh, I see what I did. I can't type, I guess. But still, it's the same concept. So it starts up, does a squiggle, comes down, and we don't really care how far down it goes right now. And then if you want to see how far down it goes, we could go look. Come on. Right there. Way down there. I'm not going to make you graph all that. And then it comes back up. And then it does a bounce and goes back down. So I know this isn't exactly the same picture, but it's pretty close. And all I want you to know is a general idea. Okay, so we're not graphing perfectly, but it does open up on the left. It does open down on the right. And it does a squiggle there. And it does a bounce there. That's good enough for me. So if you look at what we did, see, mine looks a little bit different, but it has the same types of behavior. All right, let's try another one. So now we're supposed to write a polynomial for this function. Okay. Let's go through this. First, right here, there's a solution. And it looks like a squiggle. So it's going to be of odd degree, 3, 5, or 7, not 1. And so the solution would be negative, I'm just guessing here, we don't know for sure, negative 2.5. So my factor would be x plus 2.5. And then I really don't know the degree, but I know it's going to be 3, 5, or 7, 9, 11. I'm just going to go with 3. So we're going to put that to the 3rd power. And then I see that 0 is a solution. No squiggle, no bounce, just goes straight through. So that would mean x. So now I'm going to add an x to this. And then I also see that looks like 1 is a solution. And it just goes straight through, so that'd be x minus 1. That's the factor. Let's see, this is going to be of what degree? 3, 4, 5. This is going to be of 5th degree, which is good news because down and up are opposite. But the leading coefficient is going to be positive. I think this will work. Let's go type it in and see if it works. So I'm going to type this in and see if it looks like that. Oh, I'll just delete it. X plus 2.5 to the 3rd power times x times x minus 1. You know what? It doesn't look exactly like that, but it looks pretty close, so I'm pretty impressed. We have the squiggle there, it crosses there, and if you pay attention to this graph, which I don't know how to show both at the same time, but if you look at this and then that, I mean, it's pretty close. I will say though, for the 2.5, you don't usually write it as 2.5. This would be 5x plus 2. Because if you solve that, you'd subtract 2 from both sides, divide by 5, that'd be negative 2.5. So 5 divided by 2 is 2.5. So it actually looks better like this, but if you don't know that, I'm okay with that for now. Let's do one more, and then we're done. So we have a graph. I'm going to go through, and it looks like that's negative 2. Because negative 2 is a solution, and it just goes straight through, that'll be x plus 2. And then it looks like negative 1. Is that negative 1? Negative 1 is the solution right there. So because negative 1 is a solution, the factor would be x plus 1. And then I see that 0 is a solution. That'd be x. But I see it's a bounce. So it's going to be of even degree. So it's either going to be 2, 4, 6, or 8. Just to keep my degree small, I'm going to say squared. We don't really know. And then I see the solution is 2. So that would be the factor x minus 2, and it goes straight through. Now, if you multiply all positives together, positive, 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 you get positive. So this is going to go up on the right. We don't want it to go up on the right. We want it to go down on the right. So that's why I'm going to need to put a negative out there. But let's say you didn't realize that. So let's type this in. And I really wish there was a way. I don't know if there is a way. Let me see if this works. I'm going to go type that in, see if it works. So I thought x plus 2. I think if I go here, trying something new. Okay, yeah, that'll. Oh, I tried. X plus 2, x plus 1, and then I have x squared, and then I have x minus 2. Notice it's almost the same, it just needs flipped over. So to flip it over, you just put a negative out front. And I'm glad I did this. It's easier to see both at the same time. Now, does it look exactly like it? No. Like this goes up a little bit more. This one's a little bit flatter. But I just want you guys to get a rough idea and see how factors and zeros are related. So they don't have to match perfectly, but they should have the same behavior around the zeros. And if you need to flip it over, just remember you can just change the sign out front, and that changes everything. And if I wanted to make it like skinnier, like see how that one almost matches a little bit better, maybe a 3. So, you know, as I change that, remember it makes it skinnier, but I'm not worried about that too much. I think that actually looks worse than it did before. So what I need you guys to do, and I am almost done. I have this practice. And again, the equation does not have to match exactly. And I want you to write the equation in factored form. So write me an equation that could work for that. X plus 2 times x minus 2. So I have some examples there for you to try. And then here, I know it says a lot of things, but tell me the end behavior and then draw me a picture using the factored form. And remember, you have access to Desmos if you need it, if you're not too confident. So notice another example. Another one. And another one. So these are rough sketches. I don't expect exact graphs. It's just recognizing that, like, if this is x plus 1, then it crosses at -1. And because it's even, it has a bounce. That's really the most important part of today. Looks like I'm out of time. We've finished in the perfect amount of time. Nice seeing you all. Have a good day. Feel free to sign off.